Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, predict the winner. So basically here we have an array of numbers and we have two players that are playing a game, player 1 and player 2. We just give them those names and they take turns, and we are told that player 1 starts first, so they play the first round. And both players start with a score of 0, obviously. And then at each turn, the player takes one of the numbers from the array. They can take either from the start or from the end, so from the left or from the right, okay? But only one, and then that would reduce the array size of 1 by 1, yeah? And the player adds the value they chose to their score. So player 1, for example, let's say they pick 2 at the end, and so their score is now 2. Then player 1 plays, let's say they take maybe 1, now their score is 1. And then player 2 plays and they take 5, and so this is 7, right? However, we are told that players play optimally, so that means that they will each try to maximize their score. So basically, that means in the case where player 1 chooses, let's say 2, like here, then player 2 will have to choose one of these. Player 2 will obviously decide to choose 5, okay? So that's the idea here, because 5 is bigger. And the goal of the problem basically is the game ends when there are no more elements, so all the array elements have been chosen and it's now empty. And the goal of the problem is to return true if player 1 wins the game, okay? And player 1 wins the game if score of player 1 is bigger or equal to score of player 2. So if the difference between the scores is bigger or equal to 0. Here, if both scores are equal, player 1 wins. So that's the idea. And looking here at the constraint, it's pretty small. So let's see how we can tackle it. So the first thing to think about here is the strategy to just pick the max of the left and the right. Let's say 4, maybe 1. Is not actually a good strategy, because it's not enough to determine the winner, because maybe there is a value in the middle that is bigger, and that will increase the score if we take, let's say, if we choose a bigger value, but we would have gotten 9 if we chose a smaller value, okay? And so with the absence of like sort of a greedy heuristic, then we can just and because we want to determine if player 1 can win the game in any possibility. We don't care about, like, if we just try to do this optimal way of choosing maybe the max, we don't know if there is another possibility where they would have chosen the smallest value and won the game, right? And so that means let's try all of them. So that's what we'll do. Let's try all possibilities and see which one will give us the max score. Okay, and so how do we do that? Well, let's take the smallest example here. So first, let's have a decision tree. Player 1 plays, right? So it's the turn of player 1. So let's actually have a state. Let's have turn. So this would be the turn. It's 1 if it's player 1 and 2 if it's player 2. And then we need the score of both, right? The score of the S1, the score of player 1, and S2, the score of player 2. Okay, and of course we need to also know what's remaining in the array, so let's just call it remaining. Okay, and let's actually just put remaining at the beginning, just so that you can see what this will look like. Okay, and so let's start out then with the entire array, and the turn is 1 and the score is 0 for each. Okay, so 1 has 2 choices. It can either take the first element or the last. So let's have both. If it takes the first element, then we would have 5, 2. Now it's the turn for 2. The score for S1 is 1, and the score for 2 is still 2. And then the other possibility is for it to take 2. So we have 1, 5, and the turn is now 2, and the score is 2, right? And then the score for this one is 0. So now it's the turn for 2. It has 2 choices, this one or this one. So it takes, let's say 5. Let's say it takes 5, yeah. So we have 2. Now it's the turn for 1. And then the score now for 2 is, score for 1 is still 1, for score for 2 is now 5. The other option is for it to take 2. So we have 5 remaining. Now it's the turn for 1, and 1 has still 1, and the score is 2. Okay, and we continue. Now there is only one choice, and so the array becomes empty. Now it's the for 2, but we are done. And then we increase 3, and then the score is 5. And here, player 2 wins. So here we return false. Okay, now here in this case, we have only again one choice. And so the array becomes empty, turn of 2. 1 is, the score is now 6. So here 2, and then we get for 2 is still 2. Okay, so now here we can say that P1 wins, but is this one a possibility? Is this one actually a possibility? Well, the problem says that each player plays optimally. Okay, so that means given these two choices for player 2, given these two choices, they will choose the most optimal choice, which is of course this one. So this actually would not be, P2 will not choose this, because then they won't win, right? Because it's their turn. So it's only if P1 doesn't give them any choice, right, to win, then they can they can win, right? And so that means they will choose here. And so you can already see here, when it's P2 player 2 turn, what P1 needs is P1 needs for all choices to be losing choices. If one of them is winning, player 2 will choose it because they play optimally. Okay, and so this is one of the first insight. Let's keep that in mind. But for player 2, for player 1, if it has two choices and one of them is winning, it will of course choose the winning one. Okay, and so here, using this tree here, you see that we have two choices each time. We have choice 1, where a player will choose to take the left. Okay, so take left, and choice 2, where it will take right. Okay, so now what we want to return is, if it's the turn for player 1, let's call it turn equal to 1, so this is player 1 turn, then we only need one of these two choices to be true. So we can return true if C1 or C2. So if one of those choices is true, then it will take the most optimal one, which is winning. But if it's turn for player 2, we need both choices to be losing, because like in this case, since this one is a losing choice, player 2 will only take this one. Okay, and so for player 1 to win, both choices need to be losing. Okay, so which means here that we need C1 and C2 to be true. Okay, so now with that, we can actually start doing our solution. We have the state that we need, the parameters for our state or our recursive function, and we know the two cases that we need. It's either take left or right, and then we know that depending on the turn, we choose we take either or and. And then the base case. What is the base case? Well, the base case when we don't have any remaining elements, so when the list is empty. So if not remaining, so in Python, if it's empty, what should we return? Well, it depends on the score. We just return if score 1 is bigger or equal to score 2, that means player 1 won. Okay, this is winning. One thing I want to clarify here for C1 and C2, remember this is returning true only if score 1 is bigger. And so and here means with choice 1, player 2 loses, and with choice 2, player 2 loses as well, because the state that the function returns is whether player 1 wins, which means whether player 2 loses. Okay, and so here it means whether player 1 wins and or player 1 wins. So if the turn is the turn of player 1, then if one of them is a good choice to win, they can take it. But if it's the turn of player 2, then both choices have to be wins for P1. Okay, for it to be a win for P1, because if one of them is a win for P2, P2 will take that choice. Okay, I hope that's clear. Now, what is the time complexity for this solution? Well, we are using a recursive solution where we have only 2 choices. Okay, and what's the depth of the tree? It's going to be n, because we have n elements, and each time we reduce by 1. And so, and we have 2 choices each time. So this would be 2 to the power of n, because we have 2 branches each time and we have n branches. So with n bigger or equal to 2, like in the constraint, this should be a good solution. It should pass. Yeah, so let's implement it and make sure it's good. Okay, so let's implement this solution. So what we need is our recursive function. Let's call it play. And let's pass the parameters. So the remaining elements of the list, the turn, score 1, and score 2. And we said our base case is if the list is empty, we want to return whether score 1 is bigger or equal to score 2. Okay, and then we have choice 1, which is take left. So choice 1 is take left element. And then choice 2 is going to be taking the right element. Okay, and so to take the left element, what does this mean? So basically it means you take the element at 0 and the remaining are from 1 to the end. And then what's the turn? Well, turn is 2 if it was player 1's turn. Otherwise, it's player 1's. If it was player 2's turn, then now it's player 1's turn. Now, what does the score increase by? Well, the score for 1 increases by the remainder at position 0 if the turn was player 1's turn. Otherwise, it doesn't increase. And similarly for score 2, it increases if it was player 2's turn. Otherwise, it doesn't increase. Okay. And we do the exact same thing for choice 2. So we go here, choice 2, except we want to pick the last element. So in Python, to get everything except the last element, you can do it like this. And then what we need is same thing, the turn changes, and then score 1 increases taken by the last element if we take the right element. If it was its turn, otherwise it increases for score 2, for player 2. And we said that we want if it was player 1's turn, right? If it was turn of player 1, then we want any option where they win, they will choose it and they will win. So we want to return C1 or C2. However, if it was player 2's turn, right, then we want to return both needs to be wins for player 1. Remember, C1 and C2 are true if in that branch player 1 wins. And so here, this means both branches, player 2 loses. And so, which means player 1, so this is true if, which means player 1 has to win. Player 2 doesn't have any choice. And we can actually get rid of this else just because we return here. And so now we call our recursive function, which is play, with just the array, right? So, and then the turn starts out at 1 and the score starts out at 0. So if I run this, this is C2, sorry. And looks good, let's submit. This is normal, makes sense that it's slow because it's O of 2 to the power of n. But let's see if we can optimize this a little bit. So the first thing we want to change is just make this a little bit nicer without the array. And so let's just have this be left and right. And so when we are done when left is bigger than right? So we did all of them. And then here, left increases by 1 because we just moved to the left. Right stays the same. Here, left stays the same. And right moves by -1. So still the same, we just changed the variables. And so here we need to pass 0 in the length of the numbers -1 because that's the rightmost index. Except here we need to get the element at the left. Same thing here. And here we need to get the element at the right. So, right, and same thing here. Okay. So if I run this, and this should pass. Okay, looks like it passed. Now, one thing I want to show here is that do we actually need to pass both scores? So let's try to sort of reduce the number of parameters we have here. So score 1 and score 2, if player 1, we only want to check if this is bigger, if score 1 is bigger or equal to score 2. That's the main usage that we have. So we can actually just check this, okay? So we don't need both, we can just pass the difference, right? So difference between scores with basically score 1 minus score 2, like this. So if we do that, then we can do diff. So how do we do that? Then here, it's going to be plus nums left if turn is 1. Otherwise, the difference, right? Otherwise, if it's turn for player 2, it's going to need to be diff minus nums left, because remember, we are taking the difference of score 1 minus score 2. And similarly here, except this is going to need to be right. And this should still be pass, except here we only need one variable. And we can submit. Okay, so it looks like this, this passed, okay? Now that we did this optimization, one thing we can think about is, do we actually need this turn as well, this turn variable? And do we actually need to pass diff as a parameter? Can we just have it returned and check here if it's bigger or equal to 0, right? Because why am I saying this? Because if we can return diff, then we can cache using left and right so that we don't repeat computations. Okay, because left and right each are can be at most n. So if we can make this be the state of this be 0 to n for left and 0 to n for right, then we can actually have a no n squared solution. Okay, so that's the idea here, instead of having O of 2 to the power of n. And so the idea is we don't need to do the turns, because if it's player 2's turn, since we want to maximize the diff, then we can just subtract. Okay, and so to do that, then here, let's call this choice 1. What we can do is just do left minus when it's the turn for the other player, we just subtract, because when it's the turn for player 2, subtracting minus twice is going to be adding. And so here we can just have get rid of the turn. And also, since we want to get rid of the diff, actually just return the max of the 2, because we want to maximize the difference so that it's bigger than 0. So it's best to maximize the difference, right? And so here we can just return the max for the difference. And let's just make this clear that it's a difference. Let's say diff 1, diff 2, okay? And so we take the max of diff 1 and diff 2. And here this can be, we can get rid of the turn. And since it's the subtracting the difference, we can just take the number in right minus when it's the turn for the other player, and we can get rid of this, okay? And here, this is what we already did, so we can get rid of it. Okay, and now it's a lot better. And we can, okay, let's see here, right, -1. And now you can see we have only left and right as the parameters. Okay, so let's actually pass only those two and check if the difference is bigger or equal to 0. That means player 1 wins here. Except here, since we want to return the actual difference, we only need to return. Let's change this to be equal. When it's equal, so there is only one element, we just need to return that element. Okay. And so if we submit, this passes, but we can actually optimize it further. We can have a cache. in Python, you could just use cache. If you want, you could use a memoization table, like a map that has the parameters are left and right. Or you could use also a table with the parameters are left and right. But to be faster in Python, we can just use this cache annotation. And this should be a lot faster. And you can see it already, if I submit, it quickly passes, okay? Now, what is the time complexity for this solution? Well, here, the only states, and since we cache, if we get a call again with the same values, we'll just return the cached values. And so that means here, it only depends on the range for left and the range for right. So the range for left, since left is going to be at most the number of elements in the array. So it's n elements. And for right, the n. And for right, the range is also n, 0 to n, because at most you would have the number of elements, or more accurately, 0 to n minus 1. And so, since the state of our cache is just both, at most is going to be O of n squared, time complexity. And similarly for space complexity, because we also use this cache that needs at most n squared slots, because we have n by n, then it would be O of n squared space as well. Okay, so this is a more optimal solution. And I know we went through multiple steps to understand it, but this is the actual way you solve this types of game theory or min-max problems. Is you don't need to actually be explicit about the turn. You can just basically have the difference and subtract for the opposing player and add for yourself, right? I hope this was clear. Please like and subscribe, and see you on the next one. Bye.